electronic charge and mu is the mobility. Okay, mobility is defined as B is equal to mu E, so it's a velocity. If the electric field is 1 unit, so B is nothing but mu is nothing but B. So mobility is defined as the velocity or drift velocity acquired per unit electric field. The mobility of charge carriers is determined by the rate at which charge carriers are scattered by impurities, scattered by defects in the material, and scattered by the vibration of the atoms. So these are the three main reasons which are responsible for the mobility at high temperature and in the pure material. Because right now we are talking about copper. So at high temperature and in pure material, the dominant scattering mechanism is the collision of charge carriers with the vibrating atoms. So if you increase the temperature, the atoms vibrate more vigorously and so the mobility decreases. So if you increase the temperature, mobility will decrease. Okay, and if you go back to this expression here, the value of sigma is n e into mu. In case of a metal, the value of n will remain unchanged. The value of n will not change whatever temperature you raise. The electronic charge is anyway constant, so mobility will decrease. So therefore, the net effect is the value of sigma will decrease as a increase in temperature. Resistance is inverse of conductivity, so resistance will increase as you increase the temperature. Okay. So here we talk a little bit about band theory. In case of metals, you know that the valency band is completely filled, so therefore it does not contribute to the electrical conduction. Conduction band is partially filled with the electrons, which is responsible for electrical conduction. The number of electrons per unit volume in a metal is of this order, 10 to the power 3 per cubic centimeter, okay, which is temperature independent. It does not depend upon the temperature. So the temperature variation of conductivity mu will be mainly because of the variation of mobility with temperature. So if we increase the temperature, the mobility decreases and therefore the conductivity of the metal comes down as it is heated. Conductivity sigma is the reciprocal of its specific resistance. So as the temperature increases, the resistance of the metal decreases. This is the characteristics of the metallic behavior. Okay, now we know a formula. We use a formula RT is equal to R0 1 plus alpha into T. Okay, we can also write this formula as R at temperature T to be equal to R at some reference temperature T0 into 1 plus alpha into T minus T0, that is the difference in temperature. Okay, it is the same way of writing because this expression refers to the temperature at 0 degree centigrade, and here we have two different temperature. RT is equal to RT0 1 plus alpha into delta T, and this alpha is called TCR, or temperature coefficient of resistance. Okay, so okay, so alpha is defined as 1 over R T0, RT minus R0. In this simple expression written here on the blackboard, we used to find out the value of alpha. So it's very simple experiment. What we do is we are going to measure the resistance of copper as a function of temperature, and from here, from this formula, we can find out the value of alpha. Okay, what we need in this experiment is, you are already familiar with the furnace, because we presented one experiment based on the furnace yesterday. So we need a regulated power supply to drive this furnace. These are the terminals of where we have to connect the regulated power supply. We need a temperature controller, we need a furnace, okay, and we need an insert. The insert is just like this. Here you are going to use 3 inserts of this type. One insert for study experiment, that is a copper constant thermocouple, and the diode as a sensor. The second experiment is in fact PCR of copper and energy band gap of silicon. This insert is for this particular experiment, and there is third insert also, which will be for verification of QB bias law for a ceramic and polymeric capacitor. Okay, so I will explain you what exactly this is. Yesterday I explained. So for this experiment, B use a fine copper wire of gauge 44. Copper has a room temperature of 3.3 ohm per meter. So what has been done in this experiment? 10 meter wire of a long wire of copper has been taken. It is wrapped onto an insulating tube and fitted into a hole on a rectangular aluminum block. This is a rectangular aluminum block. It is common in all the experiments. Okay, so for this particular experiment, a insulating stand has been taken and the copper wire, 10 meter wire, and it has been inserted here. You can see 4 terminals coming out, 2 for the voltage measurement and 2 for the current measurements. So it has been inserted, and the white thing, this is a Teflon tape just to insulate everything. You can see even the leads are also, in fact, they are wrapped with Teflon up to this place so that there is no shorting, they don't touch each other. So we have a block, okay, we have a block carries on this, we have a platinum sensor, okay, so these are the terminals, everything is written here. So we have the terminal for platinum sensor, so we have a sensor inside, okay, that senses the temperature, we connect our temperature controller here, so therefore by using these 3 terminals, we can measure the temperature inside a furnace by using a temperature controller, okay. So we are using now a 4-way, again a 4-terminal arrangement is used to measure the resistance of a copper wire. So here if you look at this data, the resistance of copper wire is 3.3 ohm per meter. Okay, so we are using 10 meter of a wire, so therefore the entire wire will have a resistance of around, this wire has a resistance of 33 ohm. So what we do, we connect our temperature ends here, so we allow a current to pass through, okay, and then we have in between, we basically have 2 voltage terminals. It is a 4-pole arrangement again, and we measure the voltage across this range here. Okay, there was some confusion about the 2 probe and the 4 probe yesterday. Let me clear it. Suppose you are having a sample like this. What you are going to do is, your 2 probes will be just like this. You are having 2 probes like this. So these probes, you are basically allowing a current to enter into the sample through 1 probe, and the other probe, the current will come out. This is the sample. These are basically the 2 probes in 2 probe method. So you allow the current to enter, and at the same time you are putting a voltmeter also here only, because 2 terminals are coming out. So these are the 2 terminals. Okay, so these are for current, and we are going to connect a voltmeter here also. So therefore we can't avoid the current to pass through the contacts. Is this clear? Okay, because we are, see, 2 probes are there. You have basically a sample. What we are going to do is, we are putting 2 probes. These are the probes. So the current will go inside, the current will come from this probe. Now where are we going to measure the voltage? We are going to measure the voltage here only. So that means whatever voltage we are going to measure, it is the voltage drop across this contact, over this length, and across this contact also. But in 4 probe, the current is going like this. Okay, the voltmeter resistance matters here very much. If the resistance of a voltmeter is much larger than the resistance here, a very negligible current will pass through. So we can assume that current to be negligibly small, and therefore the chances of drop across the contact resistance will be comparatively reduced. Not exactly reduced. Exactly means the resistance must be infinity. So here in this case, we have basically so this is the case. So we have a copper wire. It's 10 meter. So 10 meter corresponds to 33 ohm. Okay. These are the 2 voltage leads. The voltage leads, the resistance between the voltage leads is of the order of 20 ohm. Okay. What we will do here in this experiment? We allow a current of 5 milliampere to pass through. So we set a current of 5 milliampere here through the current leads. So you can see here also, okay, there are 4 leads which are coming out on this. Here itself, 4 leads are, 2 wires are coming out. 1 wire consists of 4 probes, so 2 for current and 2 for the voltage. And here on the top, you have these 4 terminals. These are for current and these are for the voltage. So you are going to connect your current source across the 2 extreme ends, okay? And the voltage you are going to measure about this. So these 4 terminals are for TCR of copper. These three terminals are for platinum resistance thermometer, and these three for the other experiment on band gap oscillator. So we have this resistance is roughly of the order of it's around 20 ohm. Okay, and this data 33.3 ohm, 3.3 ohm per meter. This is the data at 0 degree centigrade. So the temperature at room temperature, the resistance will be slightly larger than this. Okay, the value of alpha for copper is 0.003 degree centigrade per degree centigrade. This is the value of alpha. Okay, this is what you are going to calculate. This is the theoretical value I am going to quote. So here, if I allow a current of 5 ampere to pass through a wire between our voltage ends, these are the voltage leads, the resistance here is 20 ohm. So we expect a voltage of 100 millivolt, 20 multiplied by 5. So 5 is 100, so it's 100 millivolt. So voltage across the voltage leads is of the order of 100 millivolts. Suppose now we raise the temperature by 10 degree centigrade. When we raise this formula, we now allow a current to pass through. So what we can do mathematically, we can multiply both sides by I. So it becomes IRD is equal to IR0 1 plus alpha into delta T. IRD is the drop across the two voltage leads at temperature T. This becomes equal to the drop BT0 into 1 plus alpha into delta T. Okay, mathematically we have multiplied, otherwise we are measuring the resistance by measuring the voltage. So here, if you raise the temperature by 10 degree centigrade, by applying the same formula, right now it's 100 millivolt. So 100 millivolt to 1 plus, we are raising the temperature by 10 degree Kelvin or 10 degree centigrade. So this is 10. The value of alpha is 0.0043. If you calculate this, it comes out to be around 104 millivolt. This is 100. Okay, 100 into 1 is 100. 100 into 1 is 1000. So decimal comes here. So this becomes 104.3. So therefore, if you increase the temperature by 10 degree centigrade, the voltage will increase around 4.3 millivolts, and we can easily measure this voltage by normal multimeter. So same thing we are going to do is here we are, in fact same thing is written on this. Okay, so it has a room temperature resistance of around 20 ohm at room temperature. A current of 5 milliampere will give rise to a voltage drop of 100. Such a voltage can be easily measured. A rise in temperature of 10 degree centigrade will produce 4.306. So it's 4.3 millivolt. Okay, this can be 6 also, because we are quoting this data 3.3 at 0 degree centigrade. If the temperature increases, suppose this 1 here, 100 becomes 101 or 102, then the 6 volt change can also be justified. So these are measured by digital multimeter. So aluminum block with a copper wire is suspended. So what we do is, you know about the furnace. So we suspend it, there is a support, so we suspend it so everything goes inside the furnace. To avoid the losses due to convection, the open end of the furnace is basically just we fill some cotton so that the convection current does not go inside and the loss due to convection can be avoided. Similarly, when you want to cool down, then you have to remove that cotton pad. So here in this case, the furnace is heated by passing a current through a regulated power supply. Again, similar to the previous experiment that we discussed yesterday in the afternoon, the voltage of the regulated power supply is adjusted in such a way so that the temperature at the center of a furnace increases slowly at a rate of 1 degree centigrade. Even if you are in hurry, okay, you have to follow this, otherwise you will not end up with the right result. Okay, so I am repeating this because suppose in the afternoon around 3 or 4:30 you are in hurry to run to your home, okay, and you increase the voltage to 12 volts. You will get the readings, but the readings will not give you the right result, and Professor Srinivasan will ask you to repeat the experiment next day. So you have to regulate the temperature in such a way so that you can get the temperature rise of 1 degree centigrade every minute. 1 to 1.5 degree centigrade per minute. So you have to begin with a voltage of around 7.5 volt. That you will find out already there onto the panel. When you will switch on, okay, you will see a voltage of 7 or 7.5 volt. What you have to do, you have to increase and a voltage of 8.5 here, 8.5 to 9 volt is required to get a temperature of 100 degree centigrade. So you have to start from the room temperature, let us say 35 degree centigrade, you raise the temperature by 10 degree centigrade and find out the voltage across the two leads. Okay, so we connect a constant current source to the current terminals of the copper coil fixed on the terminal block, two extreme ends. The current is said to be 5 milliampere. The voltage terminals of the copper coil are connected to a digital multimeter. So we connect a digital multimeter between these two ends. Okay, and the temperature of a furnace is read from the temperature indicator of the controller. For every 10 degree change in temperature, the digital multimeter reading is taken. So what we do here is we are basically taking the reading, we are recording the reading of voltage as a function of, so we are recording temperature here 35 degree, 45 degree and so on, and we are recording the voltage at temperature T. So finally, once we take these readings, we are going to plot a graph. We plot a graph with the temperature on x-axis and the voltage on the y-axis. This equation Vt, so we can write it as Vt to be equal to V0 plus V0 into alpha into delta T. Okay, so we are going to plot a graph between V, T and V0 1 plus alpha T. So we are plotting a graph between V and alpha T. If you compare this with y is equal to mx plus c, that is the equation of a straight line. So x is delta T, y is Vt. So we have V on the y-axis, delta T is on the x-axis. So if you plot a graph, what we are going to do is we are going to measure the slope of a graph, and at the same time we are going to measure the intercept made by the straight line onto the y-axis also, because slope is V0 alpha. So slope here is V0 into alpha and the intercept here is V0. So finally we divide the slope by the intercept to find out the value of alpha. So it's a very simple experiment. But it's time consuming because it will take some time for the temperature to rise. So how to set the current for TCR meter? You are familiar with the constant current source. So put both ranges to the low, because we are working with the low current mode, 5 ampere to the low current. Adjust the setting knob to the minimum position. Connect the copper wire terminals to the output terminals of this one. These are the output terminals. So these terminals are connected to the current leads here onto this insert. Then switch on the means. Adjust the current to 5 milliampere. Measure the voltage across the two terminals with DMM. Okay, and then you have to take the readings like this. Here, this is the current. Okay, so yesterday I was trying to tell you about standard deviation, but we were not able to. I was not able to show you the data. The way it is described in the manual. If you are using origin, you can find out everything directly. The origin will give you the moment you plot a graph. Okay, between the voltage and the temperature, you get everything. You get the slope, you get the intercept, you get the equation of a straight line, and you get the standard deviation also. But if you are working with Excel, okay, then you have to move like this. This is V that we have measured. What we do now is we are going to fit a straight line, and equation of a straight line we can find out by using origin or Excel. What we do, we make use of that best straight fit, and we again calculate the value of a V, because straight line may not accommodate all these points because it is the best fit. So what we do on that straight line, y is equal to mx plus c, we are going to substitute these values of the temperature and we calculate it. So this is measured from the experiment here. This is the calculated value by using the best fit here. Okay, finally we take the difference of these two readings and take the square. Error means the difference between the measured value and the calculated value. Then we add all these errors here and take the sum of these errors is called variance, and the sum of all these errors divided by n minus 1, where n are the number of readings, is called variance. So this is the variance, and if you take the square root, then this is the standard deviation. Okay, so if you are not comfortable with origin, you can work out this exercise also, so that you can calculate the standard deviation just to know the accuracy of your measurement. Okay, so slope of a graph comes out to be this one, the intercept comes out to be this one, and the value of alpha is slope upon intercept, so it is 4.64 into 10 to the power minus 3. For pure metal, I hope this is for pure, so it's close to this. So that is the first part of the experiment. Okay, along with this, you have to perform basically both the experiments simultaneously. What has been done here in this case is, we take before we go to the theory, okay, we are going to measure again the resistance of a chip. We have a semiconductor. This is a semiconductor chip that is also pasted here. Then there are two terminals, two copper wires are just contacted here. They are in contact, and the contact is made by silver pen. Okay, so these are the two contacts. What we do now, this chip is somewhere here. We have the terminals here. Let me check. Yeah, we have terminals here, and between these two terminals, we have an external resistance that also you can see inside. We have a resistance. So what is done? These two terminals are inside because we are heating this. So our semiconductor is inside. We connect a small resistance, small r, in series with this. So our sample, our silicon chip is inside. Okay, the two wires, one wire comes to this, and this wire is connected to a 9-volt supply. This is 9 volt. I'll call this as V0. So we are having a silicon. This is a semiconductor. This is a semiconductor. It is connected in series with a resistance. This resistance is 470 kilo ohm. This is known. Okay, you can read from the color code given at the back. So this is outside. So there are three terminals. These three terminals are for platinum resistance thermometer. These four terminals for TCR of copper. So we are still left with three terminals. Between the two terminals, we have a connection from the chip. And between the other two terminals, we have a resistance R. So what we do, we apply simple Ohm's law to find out the current. Current will be equal to V0 divided by small r plus capital R. Capital R is the resistance of a chip. The resistance between these two ends is of the order of mega ohm. It's very large. Okay, so I is equal to V0 divided by small r plus capital R. What we do here is, between these two terminals, between the external resistance that we have outside at room temperature, we measure the voltage. So we are going to measure the voltage across the known resistance 470 ohm as a function of temperature. So in this case, here you are taking the reading because you are heating both the samples simultaneously. What you have to do, you have to make two tables. Okay, one for TCR of copper and other for energy band gap of silicon. And what you have to do, you have to measure V as a function of temperature. V as a function of temperature. Why V? Because I is equal to V0 upon R plus R. The value of a V is equal to I into small r. The value of I is, so this is V0 into small r over small r plus capital R. Okay, we can, this is V, so this is V upon R, V0 upon V. We take this V onto this side, V0 upon V, it becomes 1 plus capital R over R, V rewarded. Okay, so V0 divided by V is R plus R over R, so it becomes 1 over R, V0 upon V minus 1 into small r is capital R. So we are going to measure this V. but we will make small r is known 470 kilo ohm. So small r is known. We are going to measure the voltage across the known resistance of 470 kilo ohm as a function of temperature. Okay, but by making use of this simple formula, we are calculating the value of R of the chip, of the semiconductor chip as a function of temperature, and that will give us the energy band gap of silicon. Okay, let us see what is the underlying feeling. So if you recall again, sigma is equal to rho into N into mu. In case of metal, N was constant, E was constant, the variation in sigma was because of mu only. But in case of semiconductor, N is also not constant. If you raise the temperature, more and more electrons jumps from conduction, sorry, valency band to the conduction band. Okay, so here in this case, the temperature dependence arises from the temperature dependence of N and mu both. If you go into the theory, the mobility term is T to the power of minus 3/2. Okay, there are variety of scattering mechanism. Okay, I will not go into the details, but you must have read about this formula. It is ATQE to the power minus EG over KT, law of mass action in physics. You write down the expression for electron concentration, you write down the whole concentration, you multiply both of them together, take the square root, you can find out the intrinsic carrier concentration. So here mobility goes as T to the power of minus 3/2. Okay, but if we again talk about the band theory of solids, at 0 degree centigrade, 0 degree Kelvin, the highest field is completely filled and the next higher band is completely empty. That means valency band is completely filled and the conduction band is empty. And the energy separation between the top of the valency band and the bottom of the conduction band is Eg. Okay, in case of intrinsic semiconductor, the Fermi level lies midway of the forbidden gap. Even if we have a very lightly doped semiconductor, then also we can approximate this to be equal to Eg/2. Lightly, the doping is much smaller, so it is close to the intrinsic semiconductor, so we can approximate it. Okay, so then at finite temperature, some electrons are excited to the bottom of the conduction band and these contribute to the conduction, and the probability is given by e to the power minus Eg/2 into Kt. This is basically a crude way of talking about these things. Otherwise, you can recall the expression that you must have derived by some other way. So the conductivity sigma is proportional to e to the power of minus 3/2 exponential minus Eg over Kt. This is nothing but E over Kt, Maxwell-Boltzmann distribution function, the probability. And in case of E, we are taking it to be Eg/2. We are making an approximation that we have a lightly doped semiconductor. So it's a semiconductor lightly doped, but we are taking it close to an intrinsic semiconductor. So if you take the inverse of this, so resistance will become e to the power minus u will become e to the power of nu, e to the power Eg over Kt, and this is the formula which is used for calculating the energy band gap of a semiconductor. Okay, so all other things are the same. Here we are using a 9-volt cell and a DC voltmeter. We have the same insert. A small sliver of silicon is mounted on one of the faces of aluminum block. Okay, you can't see, but you have to believe that we have a silicon chip inside this. Everything is wrapped because it's ready to be inserted into the furnace. Okay, electrical contacts to the silicon sample are made by pasting two thin enamel coated copper wire to the surface of the silicon chip with silver band. At about 30 degrees centigrade, the resistance between two contacts on the silicon chip is of the order of 50 mega ohm. Resistance is very high. Because of this high resistance, a two-probe procedure has been used to measure the resistance. Not four-probe, two-probe resistance is very high. Okay, this is a 470 kilo ohm. Here we have a 9-volt. Okay, you will be using a 9-volt cell, but don't rely on this data. When you go to the lab, you have a multimeter in your hand. Please measure. In place of 9, it can be 8.5 itself. So you have to make use of that 8.5 instead of taking it to be 9-volt. Okay, then the calculation I have already explained to you. This is a This is our silicon here. This is our external resistance. This is 9-volt battery. Okay, and you now increase the temperature and measure the voltage across this resistance here. Okay, and finally by using this formula here, you can find out the resistance as a function. Okay, all these things are clear. You have to read it slowly so that you attain a temperature of 1 degree centigrade every minute. Okay, these are basically the readings. Here we increase the temperature. So this is the temperature in degree Kelvin. This is the inverse of a temperature in degree Kelvin. This is the voltage. So we are going to measure the temperature and the voltage across this resistance. Okay, this R we can calculate by making use of this formula. So we know the value of R. We take 1.5 T because the formula is R is equal to R is some constant A, e to the power of 3 by 2, e to the power of Eg over kT, Eg over 2 kT. So this is the formula. So if you take ln of R will become ln of A plus 3 by 2 ln of T. So this is minus ln of or minus 3 by 2 log of T. Okay, this is equal to 1 upon 2. Sorry, Eg over 2 kT. So finally you plot a graph, okay, between the resistance here and this ln of R minus 1.52 because this comes from the theory. So you plot a graph, you find out that
distance of silicon or semiconductor that decreases with the increase of temperature.
the distance will decrease here. Temperature is increasing. Resistance is decreasing. So temperature is coming down. In case of metals, it is other way around, it increases. Okay. So you calculate. So this is the formula. So you take the value. This is 3 by 2. From the slope, one can find out the value of Eg over K, and it comes out to be 1.21 electron volt. And you already know that silicon, the energy band gap is 1.1 electron volt. So we end up with a value close to the theoretical value. So that is all about these two experiments.
By increasing the temperature, solar resistance also changes.
By increasing the temperature?
Solar resistance also.
No, because you are. That's what I was telling you. The external resistance is outside. You have basically this thing here inside the furnace. This is outside. So this is at room temperature. So resistance is just here. Okay, so you are heating this. Okay, but you are measuring the resistance between these two things. The voltage is magnetic, that is the room temperature. That will not change. Everything is changing inside. So we can measure the resistance of semiconductor, okay, as a function of temperature. And from there we can find out the energy band. So we now have a temperature and then you have to. The next lecture is from 11. That's what